Okay, so let's talk about regular expressions now. So first of all, you don't need to memorize anything. This is like a screenshot of what what you will be given in the fall 2020. This is from the fall 2023 midterm reference sheet, and you'll be given something like this in spring as well. So just be familiar with all these operators and the description so that you don't have to think about it during the exam itself. So with that said, let's get some practice done. So I'm going to zoom in a little bit. And yeah, so for part A, which string contains a match for the following regular expression? So the character, this character represents single space. Okay, so let's go one by one. So first of all, of course, pause the video and think about which one is correct for you, but let's go one by one. So when we do 1 + 1 $sign, so the $sign, as you can see from above, $sign denotes that the character before that will be the pattern before that should match something at the end of the string. So at the end of the string, we expect at least an 11. Now, why is that? So let's talk about, so we know that we expect a 1 at the end. The plus sign here denotes one or more. Therefore, we expect at least an 11. It could be 111 as well, or it could be 1,111. But we expect 11 at the very least. So that rules out part A. And actually, that also rules out part C. Because here 111 is at the beginning of the string. Part B, however, is right because we see an 11 here. So another thing I want to mention is that this plus sign the plus sign over here will not match the plus sign over here. And why is that? Now, this is really something that is really important about regex. For all these special characters, if you really want to match the literal version of the special character, so let's say you wanted to match this plus sign, you have to use something called a backslash operator. So in this case, backslash would be just a backslash. So this just be the sign over here, and here you can use that in front of a plus sign to match the first sign, to match this over here. All right, so that was part A. Part B is very interesting. It puts all the fundamentals to work. So here you have to write a regular expression which contains only one word, and it only contains lowercase letters and numbers, including the empty string. So let's talk about the only one word part. We know that word, the string should begin with that word and end with that word. We can use the caret sign and the $sign. So at the beginning and end. So the caret sign denotes that this particular pattern is at the beginning of the string, and the $sign indicates that this pattern is at the end of the string. And then, since we are given classes of characters, lowercase letters and numbers are classes of characters. So we know that we have to do something with square brackets. Wait, let me pause. So now that we know that we have to use square brackets, we can go to lowercase letters and numbers. Lowercase letters can be denoted like this, and then numbers can be denoted like that. There is one thing missing though. This itself will only capture one character. So we need a sign which can capture multiple characters, and we need to include the empty string. So here, star would work perfectly. If we use plus means one or more. So it doesn't account for the 0 case. Star means 0 or more. So if it's 0, then it's just the empty string, which we are supposed to match. Okay, so that was so let's talk about part C. So here you're given this string called some text, and your goal is to return this list using read.findAll. So let's first understand how read.findAll works and what input it needs. So what you'll see over here is that read.findAll takes a pattern and a string. Now we have the string, we just need to come with the pattern that gives us the list of all the matches. Okay, so let's go back, and here let's work with a variable called pattern and assign it with a regex string. So before I actually write down the answer, I really want you to think about what is it that is common amongst all of these strings. What kind of format would you be able to use to capture these strings exactly? Now you should notice that all these strings start with some digits, followed by a space character, and then followed by some word characters. Now, these word characters can give different lengths, and these space characters, the number of digits can also be of different lengths. Here it's the same, but you need to be flexible enough to be allowed to allow multiple digits. So what we can use is we can use the plus sign character to account for this flexibility. And let me write this down and then explain. Okay, so the plus sign is one or more. So here you have one or more digits followed by exactly a singular space character and then a one or more word character. So that's your pattern, and then you can just pass in your pattern to read.findAll. Okay, so that's what you can do for part C. Part D is part D is a long problem, but so we're gonna work through this slowly, and I really want to fully attempt this on your own first. This is a wonderful problem to really understand these different characters. So yeah, cool. So in this question here, you were asked to specify the starting and ending position of the first match in the string. The index starts at 0, and remember that, and here we are assuming, when here for the purposes of this question, both the endpoints are included. Okay, so keeping that in mind, let's work on the first row. We'll go row by row. So looking at row 1, let me just actually reload this a little bit. Okay, so the first example is actually done for us. So let's look at why that works. So the first regex, so this is the regex string. So this is regex string, and then this is the this is the pattern, and then this is the string. And as you can see, the star here only acts on C. So it basically means 0 or more of C. And since our regex tends to be greedy, it's going to match ABC. Not technically, it matches AB as well, but between AB and ABC, it's going to choose ABC because it's the longer string or longer match. So therefore, you have 0 and 2 as the first answer. Similarly, for the exact same reason, 0 and 2 is also the answer for ABCS. The match ends of ABC. Here, however, you see that you have AB followed by a space character. So since our regex pattern matches AB, we can just say that our first match is going to be 0, 1. And then, of course, ABC will be a second match. But in this question, we are only talking about the first match. Okay, so that was, and then there's one more column. Here, you have ABC followed by a comma and some numbers. However, we just, our match ends right at the C. And again, this is 0, 2. For the same reason as columns 1 and 2. Okay, so let's see what the next part brings us. So here, this seems more complicated, but let's break this down. So you have this character class, and you have this caret sign, which basically means that you want to match everything but what is inside this character class. And what is inside this character class is a space character. So you want to match you want to match everything until you encounter a space character. And since there's a plus sign, you basically keep on going. It's one or more of these non-space characters. So since there is no space character in the first string, you essentially match all of it. So you get 0,6. Similarly, this is also, there's no space character, so you match all of it. Here, there is a space character, so you only match AB. And again, here there's a space character, so you only match the first 4 characters. So 0,3. Okay, so let's go to the third row. Here you have AB dot star C. So this is kind of similar. This might seem similar to the first row, but the dot, the period sign, actually is very very powerful, I guess, in regex. So the period sign basically means any character. So in our case, let's look at all the 4 examples. So AB.C, that this basically means that the match should start with AB and end with C. So what you'll notice is that the last C in the first column is here. So again, you only match 0 the first 3 letters. And since the period sign can be anything, and there's a star in front of it, that means there's 0 or more of the period signs. So not period signs, but any character. So since you allow for the 0 case, ABC itself is a match. So by the same logic, ABC again is a match because the match starts with AB and with C, and there's nothing in the middle. In column 3, however, you'll notice that AB is at the beginning, and then the C is at the end. So you actually are gonna match everything. And the reason for that, so you technically, actually, yeah. So in this case, you match everything. And then, and because the period sign can mean any character, including the space character, and including the AB in the middle. Okay. And let's go to the last case. Here you only match the first 3 characters, and that's just because you start with the C is the character over here. Okay, so last row. Here you have this character class where you are matching all the lowercase letters and 1, comma, and 9. That's how you're supposed to read it. So the hyphen here basically signifies what's the range of characters that you're matching. However, if it's individual characters such as 1, comma, or 9, you're only matching those characters, nothing in the middle. So keep that in mind. So in the first one, you actually match everything because it's completely lowercase string composed of letters. For the second column, you only match the first 4 characters because the exclamation point is not included in the character class. And for the third point, you only match the first 2 characters because the space character is not included, again, in the character class. And for the last thing over here, you only match the first four letters, first 4 characters, including the comma, because that's part of your character class. But you stop at the space sign because that's not a space symbol, as it's not part of the character class. Okay, so hopefully that was very helpful. Hi everyone, welcome to discussion 4 for Data 100. Today we'll be covering a lot of different topics. So first we'll do visualizations, then KDEs, and then logarithmic transformations. So let's get started with visualizations. So here you have a screenshot from the fall 2023 midterms reference sheet, and you'll see that most of the documentation has been provided to you. So you definitely don't need to memorize anything. It's just that you need to interpret, you need to know how to interpret this documentation ahead of the exam. So having said that, let's go to the first question. So the data we'll be working with is about Bigfoot sightings. Now this data set is very messy and has a lot of missing values across different columns. And for the purposes of this worksheet, we'll be dropping all the observations with any missing values. And we'll also be dropping some unneeded columns. So this is normally not a good practice as we discussed last time, but for learning's sake, we'll do this now. Okay, so here's a screenshot of the first 5 rows of the Bigfoot dataset. And the first question is asking you to look at some distributions of the individual quantitative variables. So the first question is about the first part. 1A is about what are appropriate visualizations for plotting the distribution of a quantitative continuous variable. So remember there were 4 variable types that we discussed last time, and a quantitative variable is where the intervals themselves have meaning, like the meaning stays consistent between all intervals, and continuous is where the variable can take not whole number values. Anything with decimals, for example, can be continuous. So so in this case, which of these 6 plots, and you can choose multiple, which of these 6 plots are appropriate visualizations? So I'm going to get started so by just going in order. So first of all, pie chart is not correct here because pie chart is about a categorical variable, and it's only for qualitative. So that means only for qualitative variables and understanding their distribution. Here we have quantitative variables, so pie chart is ruled out. And here, since we only are working with one variable, a kernel density plot actually works fine. So just to give you an idea what a kernel density plot looks like, it's just plotting what the density of the data points are across that variable. So this will be your continuous variable, and this will be sort of your continuous. This will be a KD plot. So kernel density plot works. Scatter plot does not work, and that's because for scatter plots you need 2 quantitative continuous variables. Here we are only working with one. Box plot also works because it only needs one continuous variable. It only needs one variable, and it can give you insights about what's the median and what's the sense of like where are the outliers compared to where the median is, and what's the general, where do most of the data points lie. Histogram also works as it is similar to a kernel density plot. Instead of having a smooth curve, you will have these blocks, and this can just give you an idea of what how many data points lie in a certain interval. And hex plot, again, similar to scatter plot, does not work for our case, and that's because you need 2 variables for hex plot. So let me write down the reasons. Need 2 variables, need 2 variables, and needs to be pie chart. Pie chart is it's for categorical variables. Okay, so that was part A. Moving on to part B. Here, you have to write a code. So you have to write a line of code where you have to produce a visualization which depicts a quantitative continuous variable distribution as shown below. So here this is a histogram, and you can also see that there's a KDE curve on top of it. And here you have the wind speed on the x-axis and the count on the y-axis. So how do you do this? Well, you can use Seaborn's methods. So let's scroll up to the documentation that we have, and we want to make a histogram and also need a KDE curve. So in our case, just a histogram, this method in particular will be helpful. So we can use that, and we need stat equals count. So I'm just gonna write it down for our case. So the code here will be SNS this plot, and here you'll specify the data frame. X, so our variable will be wind speed. And here KDE will be true. Remember, by default, it is false. So this code should give you the plot that is above. Now, in the case that you want density instead of count, so for density, just put an extra argument saying that stat equals density, if you need it for some particular purpose. But yeah, so this will give you the required plot. Everything you've done, and actually give you an idea of what all the information in a single visual. So here you can see that you have a scatter plot where you have the wind speed on the y-axis, moon phase on the x-axis, and the season are depicted with the color of the data points. Something else that you should notice that all of these data points have low opacity, which helps you understand like where points of higher density lie. So it's easier for you to tell which are the more common occurrences. So for that, let's just start with the scatterplot documentation and pass in some more parameters. So SNS.scatterplot, and we pass in data equals Bigfoot as usual. Your X is moon phase. Your Y is wind speed. And finally, here's the tricky part that how do you incorporate season data? So you can use a parameter called hue, and this very conveniently colors all the data points according to the season. And finally, to change the opacity of different data points, you can set the alpha value to be 0.2. It doesn't have to be 0.2, it can be a low number. But again, the whole purpose of that was to give you an idea of like where the higher density points will lie. Okay, so that was the visualization part, and I'll be back. Okay, so let's talk about KDEs. So KDE is basically a method to estimate the probability density from the given data, and you are given access to this bandwidth parameter called alpha, which can help you determine how much information you want to retain, how smooth of the probability density curve you want. So we'll talk about that in a second. But yeah, so before we go to the actual question, I want to mention that there are two kinds of kernels that we mostly are going to work with in data 100. Of course, exam questions can ask you about different kinds of kernels, but for now, let's talk about the Gaussian kernel. So Gaussian kernel is where you have Gaussian curve centered on a data point. So in this case, this is xi, and you're essentially modeling the probability that this data point, you're essentially saying that there can be inherent error in the data collection process. So there is some finite probability of this xi to be in this region or this region. So you're trying to model that with the KD curve. So that's the Gaussian kernel. And for the boxcar kernel, essentially you just make a box centered on the xi. And yeah, it's again, it measures the probability of uh, the new data being in that around that region. So keeping that in mind, let's go to the first question. And we talk about how you actually make these KDE plots. So you're given 4 data points, 1, 4, 8, and 9, and you're using the Gaussian kernel. And here you're also using alpha equals 1. So here your goal is to generate the KDE curve for this question. So what's the first step that we should think of? The first step that we should think of is putting the data points on a number line. So here I've done that for you. And you'll see that these are the data points on 1, 4, 8, and 9. And our goal is to use these data points to get a sense of the probability density of the data. So the first step that you need to do is make individual kernels around these data points. So I'm just going to do it very roughly here. Here. This is a very rough estimation of what the individual kernels look like. Now, there is a y-axis component to this as well, and that's the density, of course. So you do want to, so when you draw these kernels, you do want to keep in mind that all these kernels should have the same height. And how do you know this height? You can actually calculate this by setting x equals xi. So you have the Gaussian kernel formula over here. I'm just going to copy that down really quick. And so here, the maximum will be at x equals xi, right? So this entire thing will just go to 0, and the exponential will go to 1. So this will evaluate to, since alpha equals 1, this will become 1 over square root of 2 pi, which is approximately 0.4. So essentially your maximum point for each kernel is 0.4. And this is going to be updated in a second. But yeah, so that's the first step. And then so again, one more thing to keep in mind is that each of these kernels have an area of 1 for now. Okay, so the next step that you want to do is create a KDE curve, which is overall. So what you do is you sum the kernels. So again, I'm going to do a very rough estimation of what that might look like, but something like that. Now, since the area of each of the individual kernels was 1, the area of this is 4, and we do want our area of a probability density to be equal to 1. So therefore, we need to normalize this curve. So all we do is divide this density curve by 4, and it can condense to something which is more compact, just to make sure that the probability rules still apply. So I have this figure is a rough estimation, but I do have the real figure from the solution. So I'm just going to put that down. So this is, I guess, the real figure of the density curve. Okay, so this was a lot of information. Again, please post an ed if anything is unclear. Okay, so let's move on to part B. So part B is asking us to compare the results of KDEs using a Gaussian curve and a boxcar kernel. And here you have to select all statements which are true. for alpha greater than 0. So for a Gaussian, so I'll just go one by one, and because it's a select all the apply question. So for the first part, decreasing alpha for a Gaussian kernel decreases the smoothness of the KDE. So this is true. I'll tell you why. So if you look at the Gaussian kernel formula again, this is similar to the idea of alpha is here, and it's similar to the idea of standard deviation. So the higher the alpha, the higher the standard deviation. So you could think of two distribution over here. So this is highest standard deviation. So higher alpha slash STD. Right. Essentially, that's the broader curve. But when you decrease alpha, you make each of these individual kernels, sharper. So for example, if you make them sharper in the first part, you'll see that you might not see this overlap region over here, and this might just go to 0. And when it goes to 0, you'll see peaks like something like that. So that actually decreases the smoothness of the KDE. So therefore, part A is correct. Part B is asking about the Gaussian kernel being always better than the boxcar kernel. Now, this is false. And the reason for that is that it really depends on the choice of alpha. The choice of alpha can really tell you how much information you want to include, and also like what the probability density curve looks like and whether it's meaningful. So B is wrong. C says that because the kernel is smooth, we can safely use large alpha values without worrying about the actual distribution of data. Now, C is false as well. And this is because if you use a very large alpha value, then essentially in your individual kernel, there'll be a lot of overlap between kernels which are also far apart. So in the example above, there might be overlap between these kernels, and these seem like these seem far apart and visually, and we don't want those to interact. Therefore, C is incorrect. And D says that the area under the boxcar kernel is 1 regardless of the value of alpha, and that is true. And that's because the 1 over alpha formula over here accounts for the area to be 1. And okay, so that was the kernel density estimation part, and I'll be back for the logarithmic transformations part.